future evolution of the universe is going to be. And one way to do that, to understand the nature of dark energy, is to make maps of the universe. They can give us clues to what dark energy is. And so that leads me into the project I've been working on with colleagues here and around the world for a number of years, called the Dark Energy Survey. And our basic goal is to make a map of the universe, to try to understand the history of the expansion of the universe and the history of this growth of the clumpiness of the universe, in order to get at the properties of dark energy, or whatever is causing the universe to speed up. And so what we've done is we've built a camera for a telescope in Chile, and we're now conducting 2 surveys of the universe, taking pictures, snapshots of eventually 300 million galaxies over about 1/8 of the sky. And we're also taking snapshots of certain smaller regions of the sky, which we go back to and point in the same direction roughly every week to discover more of these supernovae. The Nobel Prize work was based on observations of just a few tens of supernovae. In this project, we're going to have observations of thousands of supernovae and hundreds of millions of galaxies. So we started, the survey started in late August of 2013. We just finished our 3rd observing season. It's supported in the United States by the Department of Energy and the National Science Foundation. So this is your tax dollars at work, and we are trying to spend them wisely. We also have foreign and institutional partners who have contributed to the project. And we're using this map to try to understand the history of cosmic expansion and the growth of the structure using 4 primary techniques. I don't have time to go into them in detail, but I'll just list them. One is to study these clusters of galaxies and to actually take a census of clusters, count how many of them there are in a given volume of space. A second is this technique of gravitational lensing that I mentioned before. Look at the distortions of the shapes of distant galaxies as their light passes through the foreground distribution of dark matter. A third technique is just to measure the distribution of galaxies in space, what we call large-scale structure. And the fourth is the technique that led to the discovery of cosmic acceleration, these supernovae, but just to measure many more of them, measure them more precisely, and measure them to greater distances. So I think I'll skip, so I'll just mention one of these 4 techniques. This is weak gravitational lensing. So again, the idea here is we're measuring the shapes of very distant galaxies. The light from those galaxies is traveling towards us through this foreground distribution of dark matter, halos of dark matter associated with galaxies and clusters of galaxies. And as it travels through them, the light paths get bent. That's what Einstein's general relativity tells us. And that slight bending leads to slight distortions of the shapes of those galaxies. Before, I showed you very pronounced distortions of the shapes of galaxies. That's what we call strong lensing. But that only happens to a minority of distant galaxies if they happen to be just near the line of sight to some foreground galaxy. All galaxies, all distant galaxies, get weakly distorted, weakly lensed. And so we can measure this by using the shapes of these 200 million distant galaxies. And that will give us information on dark energy. So in order to do this project, we've built an international collaboration. We have 400 scientists from around the world. The project is led by a team here at Fermilab in the US, but we have collaborators in England and in